How are we doing?
Wonderful.
Wonderfully? Good. What questions do you have? Test Monday, right? We're going to finish off these laws of logs today, and then we'll get into solving equations. Do that today and do that on Friday, and then exam on Monday. Yay! All right. So remember again, just a remind from last time, I'll write it off to the side here. If we have a log of a product, how do we rewrite that? No. How do we rewrite it? Good, right. Remember that it turns a product into a sum. So if it's a quotient, what does it turn into? Good. Quotients turn into differences. And if I have a power on the inside, what can I do with the power? Bring it in front. Good. So these are the three big properties that we're going to use for logs to help us rewrite, either break it apart or put it back together. And both skills are important. Being able to combine into a single log is going to be important for us when we solve equations later on. Being able to break it down into pieces helps us simplify things. Like I said, it gets rid of products and makes them into sums, gets rid of quotients, makes them into differences, and those kinds of things. All right, so let's look at this last example. What do you notice first? What operation do you notice first on the inside of the logarithm here? What's kind of the big operation going on first? Division, right? So we can rewrite this as log base 2 of y squared plus z minus log base 2 of 16x to the fourth, right? Log of the top minus the log of the bottom. Let's look at this first term first. Can I do anything with that first term? What's kind of the next operation that you see on the inside? Addition. Do we have any properties of logs that allow us to do anything with addition? On the inside. Do we have any properties that allow us to do anything on the inside? No, that was one of the be careful ones, right? I can't do any, even though it's tempting to take that log and put it here, right? Can't do it. This is stuff. This is as good as it gets. Okay? Please don't do anything with this. You can't do anything with it. When there's a plus or a minus on the inside, you can't do anything with it. It just is what it is. It's as good as it gets. Okay? What do you notice in the second one? What kind of operation do you notice with those two? What's going on with the 16 and the x to the fourth? What are you doing with those two things? Multiplying. So how can you rewrite that piece? What can you do with that part? Good. Okay. Notice I put parentheses around that sum because, again, that minus sign applies to the whole log. So it's going to apply to the whole thing that we rewrite it as. Okay? In that second term here, what can you do with the 4? Bring it in front. Good. And if you want to distribute the minus sign through, you can. That's okay. What questions do you have on that part? Are we okay with that? There's one more thing you can do. Does anybody else see anything else that we can simplify? The log to a 16 is something we can simplify. Or erase this so I can write it off to the side a little bit clearer. Maybe I'll erase it. It's taking forever. All right. So let's just do it off to the side for the log base 2 of 16. Remember how we simplify those? Just set it equal to x, right? How would you rewrite that? Yeah, 2 to the x equals 16, and then what do we try to get on both sides? Same base, right? What base is going to work here? 2, because 16 is 2 to what power? To the 4th. Good. And so x equals 4. Great. Exactly right. Yep, setting those exponents equal to each other. Okay? So going back here to finish this last part off, I can replace that log base 2 of 16 with 4. Is okay? What questions do you have? All right. Well, let's play around with the next few problems here, and then we'll talk about what's referred to as a change of base formula. This one is just recognizing that logs and exponentials are inverses of each other. That's the idea here. Okay? So remember for inverses, I'm going to write it generally off to the side. If I take a function and compose it with its inverse, what should I end up with? Or vice versa. It doesn't matter which way I do it. As long as I can plug the numbers in. What should I end up with in both cases? It should end up with what value should I end up with, or what letter should I end up with? The x, right? Remember, inverses undo each other, right? I should end up with the same thing. I should end up where I started, right? Both of them end up at x. Now I got to make sure that I can actually plug my x in appropriately. Okay. But in general, that's the whole idea of inverses, right? They undo each other, correct? Remember again that exponentials and logs undo each other, right? So they're inverses of each other, so they undo each other. If I did log base A of A, okay, don't write then. Go away, clear, go away. A to the x. Remember, a to the x is one function. Log base A of something is one function. These are inverses of each other, right? They undo each other. So I should end up back at x. And vice versa. If you do A to the log base A of x, I should end up back at x again. Right? They undo each other. So let's look at this first example over to the left here, part A. What should I end up with when I'm done? So there's not an x in this case. What's the letter? What's the R, right? The R is where the x is, isn't it? Okay. Now remember again, what are logarithms? Exponents. Good. Great. You remember. Cool. All right. Remember what the question is asking you. When I see log says what exponent? Right? That's what you think first. What exponent? What exponent on the base, on B, gives me B to the exponent of R? Well, what's the exponent? It would be R, isn't it? what power on B gives me B to the R? That's the R, right? They undo each other again. All right. All right. Let's look at the next one. I'm going to write this off to the side first so it's not all in the exponent all the time. What can you do here to rewrite this as a single log? What would I do first? Combining everything back into one thing. What would you do first? Okay, good. Remember, it's a sum. We can rewrite a sum as a product, right? Sum of the logs is a log of the product, right? So it'd be 5 times the x. I'll put it in parentheses to emphasize that it really is on the inside. Now what can you do with the 2? Make it an exponent. So that's natural log of 5x squared, like that, right? Because it goes up as the exponent on what's on the inside. So let me go back over here. I would have e, remember I was playing with the exponent, right? Okay, so I've got e to the log of 5x squared. What, remember when we write natural log, that's log base what? E, right? We understand it to be e. So e and natural log are inverses of each other. That was the whole reason why we defined the logarithm, right? The inverses. So I've got a function and then its inverse being composed. So what should we end up with when we're done? Let's look over here to the side again. What happened here? Yeah, the A and the log A cancel each other out, right? So what should happen over here? Yeah, it's 5 just the 5x squared. Exactly. They just cancel each other out. That's exactly right. Work on the next one for a minute. See if you can figure out what's going on there. And then we'll chat about it. Doing that. And now the next handout, even though we're. I know that one more page here, but I'll do that while we're working. All right, let's go ahead and chat. I'm doing to attack this one like I did the previous one. Let's look at the exponent, see if we can write the exponent a little bit more simply, and then put it back on. What can you do first with that 3 log x minus log 2? What should you do first? Which piece should you work on first? So notice I've still got an x, I got that in front, don't I? So I probably should take that part first, right? Okay, so remember that it's said when we do division, it would be log a base x minus log base y, right? Log base a of x minus log base a of y. Notice that there's no coefficient, there's just a coefficient of 1 there, right? I got to take care of the coefficients first. Notice the difference here between this one and the previous one was what? I got parentheses, don't I? Okay. So if we take care of the 3 first, what would you have? Yeah, so log s x or log of x cubed minus log of 2. Why is that skipping so bad? Right? And now we can do division and make it righted as what? Log of what in this case? Yep, x cubed over 2. Good. But again, we have to make sure we take care of the power first, because I have to have a coefficient of 1 in front of both of these before we can use that minus the subtraction property there. All right, so this was on the exponent, right? So right now I've got 10 to the log of x cubed over 2. But when we write log by itself and no base, what base are we assuming? 10. So the 10 and the log are what? Inverses. So what's this going to simplify to? Good, x cubed over 2. Exactly. So again, the process here is to rewrite it as a single log, and then notice that we have the inverse property of each other. All right. This is going to come up when we solve equations here in a little bit. All right. Questions? Let's look at this next one. The next one is just playing around with properties. Now be careful on these. This is not saying that A is 2. This does not say that B is 5. This does not say C is 7. It says that if I take the log base B of 2, I get the letter A, and then so on down the line. The idea is to play around with the properties to rewrite this in terms of those things. Okay? So I want to rewrite what I have on the inside in terms of the insides of the things that I know. So looking at this one, how can you relate 10 to 2, 5, and or 7 using products or quotients for powers? How can you relate 10 to 2, 5, and or 7? What is 10 equal to? 2 times 5, right? So I can write this as log base B of 2 times 5. If I'm doing multiplication now, since I have a multiply in the inside, what can you do? How can you rewrite that? Yeah, it's addition. Good. You log base B of 2 plus log base B of 5. According to what you're given, what is log base B of 2? What do they call that? That's A. What's log base B of 5? Capital B. There you go. So it's just asking you to write it in terms of the A and the B. Okay? Okay. So notice again here we wanted to get it as either log base B of 2, log base B of 5, or log base B of 7 by itself, right? What can you do in the next one? Again, we've got a square root. How can you always rewrite radicals as? Yeah, the powers, right? The negative would be a reciprocal, right? Yeah, yep, you're good. The square root would be a 1/2 power. Why is that helpful here? What can you do with the 1/2? Why is it good here? Yeah, fine. Did you say? I thought you said something. I'm sorry. What can you do with the 1/2? You got an exponent inside. What can you do with it? You bring it to the front. Good. And do you have a letter that gives you log base b of 7? That's c. So this will be 1/2 c. Your answers here should not have a log in it at all, by the way. Okay. All right. Let's look at the next one. What do you notice first on the inside? Division. How can we rewrite division? Subtraction. So this will be log base b of 5 minus log base b of 14. Log base b of 5 is that's good, that's b, right? Okay, capital B. Let's look at the log base b of 14. Treat it like we did that log base b of 10. Do you see how to rewrite 14 in terms of 2, 5, and or 7? And 7 times 2, good. So I can have log base b of 2 times 7. So how can you rewrite the log base b of 2 times 7? Very good. That's the a plus c. That's exactly right. Because it's log base b of 2 plus log base b of 7. And then we can plug in our letters, right? Log base b of 5 is b. Log base b of 2 is a. Log base b of 7 is c. What questions do you have on any of those? I'll leave that last one there for practice. It's a good practice one because it's got lots of different things, right? Okay. I'll leave that last one for practice. Let's talk about the last thing on this handout, and then we'll go on to the next one. This is a formula that you use when you need to find a decimal approximation for something where you don't have a button on your calculator. Okay? Your calculator, again, has 2 buttons, right? It has LOG, which is base what? 10. And LN, which is base E, right? Those are the only 2 buttons you have on your calculator. So if you wanted me to do something like part A here, where it says log base 7 of 3, you don't have that button on your calculator, right? Right? So we need to do something with this. That's something that we do is what's referred to as a change of base formula. You can change any log function into any other log function that you want. Okay? So you do the log of the inside and you do the log of the base and divide them. And it doesn't matter what base you use. Okay, that's why I put a little C in there. Literally doesn't matter which one you use. You can use any of them. It'll all turn out to be the same. Okay. So in particular, the 2 that you would use are what? Again, I told you that you want to use the buttons on your calculator. So the only 2 you would ever use for this formula are 10, use LOG, or LN. It's the only 2 you would ever use. Okay? No reason to use any of the other ones because the whole point of this is to be able to put in your calculator. Okay? So, if I look at this, you can do LOG of 3 over LOG of 7. Or you can do ln of 3 over ln of 7. You'll get the same answer when you type it in your calculator. Okay? When you type these in, if you've got a calculator that does something like, if it puts a parenthesis there, make sure you close it off first if you're typing it in that way. Okay? You do not want the division sign inside the log function. Okay. Did anybody do that approximation? So what others got? You might wrap. What did you get for your next decimal place after? Yep, you're good. Yep, you're right. And if you used LOG or if you used LN, you should have got the same answer. Okay? Same idea on any of these. It doesn't matter what it is. For the next one, you could write it as LOG of the cube root of 11 over LOG of 1/4, or ln of the cube root of 11 over ln of 1/4, either or. These are more exercises, just making sure that you can plug things into your calculator. If I write it with ln's, you probably, if you don't have a cube root button, I could do it to the 1/3 power, right? Cube root and 1/3 power are the same. Just make sure you put your parentheses in the right spots. That's important. But again, it doesn't matter what, don't mix and match your buttons. You can use log both times or use ln both times. Don't use log for one and ln for the other, then you'll get messed up. Okay. Anybody get a value for that?
Zero, 5, 6, 7.
So what others got? Yeah, cool, good. That's it. That's all there is to those. You can get them in your calculator. That's the goal. Okay. Any questions on that at all before we go to the next one? I know there's one more part. The next one, if you do it correctly, you should get something a little bit bigger than 2. Okay. All right. Any questions on that at all? No? All right. So let's get into our next section, which talks about solving exponential and log equations. So we're going to have, well, the first part is going to be talking about solving exponential functions. The second part will be talking about solving logarithmic functions. We've already talked about basically solving exponential functions in this fashion when we were talking about simplifying some logs. Remember when we were talking about trying to simplify logs, the first thing that we did was put it in exponential form? What was the next thing we did? Tried to get what on both sides? Same base, right? That's exactly the method we're going to do for these types of problems. If you can easily express both sides in terms of the same base, that's what we're going to do. So let's look at this first problem. We've got 5 to the x equals 25 to the 2 minus x. Do you see a base that you can use on both sides? 5? Because you can rewrite 25 as 5 squared. Good, exactly. So we have 5 to the x equals 5 squared raised to the 2 minus x. What should I do on the right-hand side? Multiply your exponents, right? And don't forget to distribute. You'll have 5 to the x equals 5 to the 4 minus 2x. Make sure you distribute that 2 through. Do we now have the same base on both sides? What can you do then? Exponents are equal. We're using that one-to-one property again, right? If the outputs are the same, the inputs must have been the same. Now what do we do to solve this for x? Add your 2x over, and then divide by 3. You get 4/3. Yes. Yep. Doing a plus 2x on both sides. That's exactly right. Yep. That one okay? What are we gonna do in the next one? Okay, good. Okay, I can rewrite 16 as a power of 4 easily, can't we? At least I hope so. Yep. So you get 4 squared raised to the 2x power. And again, then what can you do with your exponents? Multiply them, good. And now that you have the same base on both sides, what can you do? So the exponent's equal, right? So now we have x cubed equals 4x. Be careful. What's tempting to do? Look, divided by x is pretty tempting, right? Don't do it. You'll lose the solution. Okay? Remember again, we got a polynomial equation. Our big technique for solving any equations that have polynomials is to set it equal to 0 on one side, right? Subtract your 4x. Don't try to divide by a variable. That tends to be bad because you might lose solutions. Okay? So move your 4x over. Do you see anything you can factor out of the left-hand side? Do you see a GCF to start with? X leaves you with x squared minus 4. How does that factor? Good, that was the difference in squares. Good. And now, what solutions do you see? And what makes that piece equal 0? Yeah, good. So that's 0, that's -2, and that's a 2, right? This is why I said you don't want to divide both sides by x because you'll lose that 0, right? You'll lose that 0 solution. Work on the next one for a minute, and then we'll chat about it. That's perfectly fine. A couple of you I saw that just did it all at once. But how do we rewrite the fraction to move that 36 up? I could write a 36 to the -1, right? We use that -1 exponent to make it, that base kind of be up on top again, right? Now I want to try to get the same base on both sides. What do you think we might want to use? 6, because 36 is 6 squared. And then what can you do with your exponents? Multiply. Now, some of you I saw went directly from here to here, and that's okay. If you can do that, that's perfectly fine. Okay. Saw that 36 was 6 squared and knew you need to do a negative to bring it up to the top. That's perfectly fine. Now that we have the same base on both sides, what can we do? Set them equal, set those exponents equal. What do we need to do with the 2? You gotta add it over, right? So we have x squared minus 3x plus 2. And how does that factor? Yeah, x minus 2 and x minus 1. So then we should have our solutions of what? 1 and 2. Good. Yep. So again, here the goal is to make sure that we get the same base on both sides. So let's see what happens if we have different things. So I'm going to leave the next 2 for practice because the next 2 should just be like what we've been doing. I'm going to skip over this one for the time being and go to the next one, and then I'll come back to this one. Okay? All right. All right, so let's say we look at this one that says 32 to the x minus 3 equals 1/8 to the x squared plus 1. Again, we want to get the same base on both sides. Can we, if I don't worry about the 1/8 to start with, can you easily write 32 as a power of 8 or 8 as a power of 32. Is that an easy thing to do? Like, for example, 8 squared is 64. It's already too big, isn't it? And trying to make it get smaller is really hard, isn't it? So there's nothing easy that we can do to make one side look like the other. Can you do something though and get both sides using the same base? Do you have a number that might work for both sides? So let me think about my powers of 4. 4 squared is 16, and then it goes up to 64. So 4 doesn't work very well. Let's try a 2? Yeah. All right, because 32 is what power of 2? 2, 4, 8, 16, 32. So it's 5. Yeah. So we have 2 to the 5th. How can you rewrite your 1/8? 8 to the power of -1, and then 8 is what power of 2? 2 to the third, right? So I can write that as 2 to the -3rd if I do it all at once. If you need to do it in steps, that's fine, but that would be all at once, right? The negative flips it over, and 8 is 2 cubed. Now we have the same base on both sides, don't we? Yeah, okay. Now, next, multiply, good. The exponent on the left-hand side is 5x minus 15, good. The exponent on the right-hand side is good. Just screw that -3 through. And now that we have the same base on both sides, we can just set them equal, can't we? Okay. So we'll have 5x minus 15 equals -3x squared minus 3. Yep. Okay. Again, we have a polynomial equation, so we'll want to move everything over to one side, right? Let's add the 3x squared over and add the 3 over. So you got 3x squared plus 5x minus 12. Again, you should try to factor it if you can, because factoring typically is easier. But of course, if you don't see how to factor it, what can you always use? Quadratic formula, good. This one, since I have a 3x squared, I need a 3x and an x, right? Yeah. I think you can use a -4 and a +3 will work. Not to spend too much time on the factoring, but then I'll have a +9 and a -4. You may have used AC method to do factoring. You can do that too. But again, if you don't try to factor it, if you see how to factor it quickly, great. If not, use the quadratic formula. Okay, don't spend 10 minutes trying to factor something. Quadratic formula always works. Okay. So what does the first one give you for a solution? Ooh, hey. X equals, I think it's going to be a positive, right? Because we would add the 4 to the other side, so it'd be positive 4 over 3. Because if you said 3x minus 4 equal to 0, you have to add your 4, right? And then the other one will be -3. And those will be the two solutions. What questions do you have on that one? Okay, let's go back up to the one I skipped a second ago. Okay, go back up to the 27 over 8 equals 4 over 9. It looks kind of gross, but let's see if we can get there. Let's say you ignore the 4 and the 8, and if you look at the 20, let's ignore the other one. Ignore the 27 and the 9. And just look at the 4 and the 8. Can you write the 4 and the 8, both of us as the same base?
Two square, two. I was looking at the four, so I didn't.
I always look at it just the 4 and the 8. I do it, I do have the flip flop, you're right, but I'm looking at the 4 and the 8. So 2 would work for both of those, right? What would work for the 9? 3. The 9 and the 27 would be 3. So let's see if we can start there, okay? 27 is 3 to what power? The third. 8 is 2 to what power? The third. Okay. Let's look at the right-hand side. 4 is 2 to what power? To the second, and 9 is 3 to the second. Right? Agree with that? Now I kind of have the same bases, don't I? Because look at what you can do. I've got a 3 here for my exponent and a 3 here for my exponent. You can pull it off to the whole fraction, right? Do the same thing with the 2 and the 2 here. So let's do it this way. I'd have 3 halves cubed raised to the x, and I would have 2/3 squared. See what I did there? I just took the exponent off the top and the bottom, hold it out as one big exponent on both sides. What can I do with these two exponents here? Multiply them, good. So you would have 3 halves to the 3x equals 2/3 squared. Is that currently the same base? No. But can you make it the same base? What could you do to make it the same base? A negative exponent, right? If I flip one of the bases, just one, if I flip one of the bases, it would make the exponent negative, right? Okay? Doesn't matter which one you do, just only do one of them, because I want the same base on both sides, right? So if I flip let's say I flip the right-hand side, I'd have 3 halves to the 3x equals 3 halves to what power? -2, because the negative flips it, right? Now we have the same base on both sides, don't we? We agree? Okay. And now we can set our exponents equal and then divide by 3. So you get -2/3. You might have been able to do it a little bit quicker if you can see the fractions easily, but notice here I just worked with the top and the bottom separately and got to that point, right? I can see the 27 is a power of 3, 8's a power of 2, 9's a power of 3, 4 is a power of 2, so I played with that. Okay? So without going through it, because I want to do one example of another one, notice this is the same idea. If you look, I'm not going to go through the problem, I'll leave it for practice, but let's talk about it for a second. What base might you use for the 8 and the 16? 2, right? What base might you use for the 125 and the 625? 5. Yeah. And start there and play with that. Okay? So I'll leave that for practice. I do want to do one of these just real quick. I want to talk about logs, and then we will do more of these on Friday. Okay, so this is one of the reasons why we use logs. Having x's in the exponents suck. Okay? Our big technique right now is to get the same base on both sides. If I have 3 on the left-hand side and 28 on the right-hand side, you think I'm going to be able to easily get the base on both sides? No. So what we're going to do instead is undo the exponential function. What undoes e to the x? What is the inverse of e to the x? That's not quite, yes. That would be kind of like flipping base and exponent. Remember what functions did we describe that were the inverses of the exponentials? logs, right? So the inverse of E is natural log, right? So let's take the natural log of both sides. And we did this a little bit ago. The reason why we take the natural log is because why? Natural log and E undo each other, right? They're inverses. So if I do the natural log and E, what should I end up with when I'm done? They should cancel each other out. I should just end up with that exponent, right? So we end up with 15 minus 3x equals natural log of 28. Now we should be able to solve for x, right? You can get a decimal approximation for log of 28 if you wanted to, but right now I can just subtract 15 from both sides and divide by -3. And that gives me a just fine answer. So the technique that we're going to use, and we see a couple of problems like this following, the technique we're going to use to get variables out of the exponent is take the log. Okay? That's going to be our big technique for solving these. To get variables out of the exponent, we're going to take the natural log to get them down and out in front for us. So we'll do more examples of these next time, as well as talk about solving log equations. Okay. We'll see you on Friday, if not before. Remember again, review for the exams already posted on Moodle. That's fine. Okay. Ooh.
What?